Once Ørsted had discovered that moving charges, electric currents, are the cause of magnetic fields, the race was on to see if there was any other relationships, particularly the inverse relationship. Is there some way magnetism can cause electricity? And the two people that get credit for finding this are a British scientist named Michael Faraday and an American scientist named Joseph Henry. This was the early 19th century. And what they discovered is, yes, you can make electric current using magnets. So what I've got here is a coil of wire. There's, I believe, 500 loops wrapped around this thing, which is about the size of a toilet paper tube. It looks like they're touching each other, but they're painted, so they are insulated from one another. And they are hooked up to a meter called a galvanometer. And it's measuring current in microamps. So this is pretty small amounts of current. I'm going to flip my coil up so it's easier to see what's going on. I'm going to pick up the magnet and I'm going to put it inside the coil. And I want you to watch what happens. So I don't know if you saw that, but the needle deflected to the left towards negative currents. And now that I'm leaving it in here, it's not doing anything. If I pull it out, it deflects towards the right, towards positive currents. And then it stabilizes. So that was interesting. They had found out that magnets can cause electric currents. But it's not enough just to have a magnet. Current, but now no current. Current when I move it. The magnet has to be moving. So this became the opposite of what Ørsted had discovered. Ørsted says moving charge can cause magnetism. Faraday and Henry say moving magnets can cause current. So they're the inverses of each other. And this leads to an interesting idea, which is that if you can continuously move a magnet, you can continuously make current. So what would that look like? The magnet would have to keep moving up and down, basically. And as you can see, the needle goes back and forth. So this is not a current just in one direction. This current alternates. So as I stick this in and out, I'm making the alternating current electricity back and forth. And I want to try to figure out why. One thing I hope you can see, and I'll replace this magnet with a picture I've made, is that as I move the magnet in and out of the coil, I'm changing the amount of magnetic field inside. Obviously I can't put this in, but you can see at the pole the magnetic field is the strongest, where the lines are closest together. So as I move that pole up and down, the amount of magnetic field enclosed by the coil is changing. And that seems to be one of the things that makes the electricity more and more. So what we have to do is define this idea of magnetic field inside a little better. There's a better word for it, which is called magnetic flux. So magnetic flux, which is symbolized by the capital letter phi, is the amount of magnetic field passing through an area. That seems like a strange concept, but I think it's easy to see if we think back to the thing we did with the magnets and coils. I've got here two coils. One has a relatively small area. One has a large area enclosed by the coil. And I've drawn a magnetic field on the board. So if I hold up this coil with a big area, more of the magnetic field is passing through the coil. Remember, X's like this signify a magnetic field going into the chalkboard. So the field here, more of it is going in. If I take this coil, only a small amount of field is able to go through. More of it is outside. So they have different magnetic fluxes. The other things that matter are the field strength. So if the field was stronger, if I had more magnetic field lines, let's say I suddenly could make the field stronger while holding the coil steady, I would have more of these lines passing through it just because the field got stronger. So that matters. We just talked about how the area matters. And the other thing that matters is the angle that the surface is at relative to the field. So right now, as you look at this, you can see a lot of these field lines, these X's, through the coil. But if I start to rotate it like this, you can see fewer and fewer. And if I get it to this point, I can see none. So this is the minimum flux for this coil. It's increasing to here, and then it would be decreasing until I got back to a minimum. Magnetic flux is the amount of magnetic field passing through an area. What Faraday noticed was that magnetic flux, and specifically how fast you changed it. Notice this term here, delta phi over delta t, is a speed. How fast are you changing either the field, the area, or the angle you're at? He said that that causes an EMF, which is kind of like a voltage. So the faster you change your flux, the more apparent pressure there is for electrons to start moving. And that's what's going to cause the current that the galvanometer is measuring. So the faster this changes, the more EMF and current we'll see. There's a couple other things to notice in Faraday's law that are important. One is this big N, that stands for number of loops. The effects on one loop of wire would not be enough for us to notice. So our coils have 500 loops, or in this case 200 loops. And you basically multiply the effect by your number of loops. The other thing to notice is this negative sign. This has to do with something called Lenz's law, which we'll talk about later. It suggests that the EMF you create and the currents you create actually oppose the changes in the magnetic field. So let's change the flux at different speeds. Obviously, I can't really change the strength of the magnetic field. I've got one magnet. I can't change the area of the coil. But what I can do is I can move the magnet in and out faster. And that's going to change the amount of flux in there. So when I go relatively slow, notice that I don't get large currents. But when I move faster, I get larger and larger currents. So that goes back to Faraday's law. The faster I change the flux, the larger EMF or voltage I get, and therefore more currents. If I could suddenly make the coil much bigger while keeping the magnet in place, we would expect to see a current as well. If I could rotate the coil while keeping the magnet in place, we would expect to see a current as well. And in fact, that is something we can observe if we use the Earth's magnetic field. So I have a compass, and it shows that north, the Earth's magnetic field appears to be pointing away from the camera. And that means there's magnetic field lines passing through this loop. In other words, its magnetic flux at the moment due to the Earth's magnetic field is as large as possible. If I rotate it, now there's no flux because basically field lines that are pointing away from the camera can't pass through it anymore. But now it's at a maximum again. If I do this quickly enough, I should be able to see a current produced. And I think you do in the galvanometer. So if the EMF and therefore the current is because of how fast you change the flux, the way I'm changing the flux in this case is I'm simply changing the angle relative to the field. So I have here, but it's a really good model of how an electric generator works. This is the basis for how we generate electricity. We're going to see that it's going to convert the mechanical energy I put into it into electric current, which is what all generators do. There's a few basic parts to it. There's obviously the crank. There's a magnet, and the reason there's a coil of wire around that magnet is it actually can be an electromagnet that can make the magnet much stronger. Most important part, though, are these coils that can spin. And notice they spin between the poles of the magnet. We've talked about the idea of magnetic flux, and that's how much of the magnetic field is in the coils. And I think you could see when the coils are like this, the maximum amount of magnetic field can get through, because you can see the inside of the coil, kind of the donut hole. When it's like this, the minimum amount can get through, because that donut hole is facing away from the magnetic poles. So as I crank this, the flux will increase and decrease, and as we've seen, that generates an electric current. I want to pay a little more attention to the direction of current. As you can see here, I've got the coil set up for maximum flux. It's perpendicular to the poles of the magnet. I'm going to turn it 90 degrees to minimum flux, and watch the direction on the meter. So, as you can see, it twitched left as the flux decreased. I want you to predict what happens if I continue to crank in the same direction now to the point of maximum flux again. So we'll go in the same direction we did before, from minimum flux to maximum. And I don't know if you were surprised that the current ended up being in the same direction. It seems counterintuitive that decreasing flux to minimum and increasing to maximum would cause current in the same direction. There's another effect going on. If we think about magnetic fields causing a current downward here, and then we rotate the armature 180 degrees, that downward has now become upward. The coil's been reversed. So these two effects together contribute to the directions we see. Basically, if we go from maximum flux pointing in one direction to maximum flux pointing in the other, we get a current one way, and then if we return to the original position, we get a current back the opposite way. Together, we get alternating current. There is a way to force electricity to just go in one direction. We can do that by moving the brushes. Right now, essentially, this brush is hooked up to one end of the coil and this one's hooked up to the other. We can move them to this other terminal where the brushes now connect to this broken piece of metal. And one brush touches one of them sometimes, and then it touches the other times. Let's take a closer look at that. So I'm going to rotate clockwise like I was before, and I'm not going to change that. But watch the galvanometer. It's never going to the right. It's always pulling to the left. It's really different than the back and forth we had before. So this actually is direct current. Although it's pulsing, there's always a positive and there's always a negative. So that's really different behavior than before, and I want to explain how. Check that out. That's a break in the metal. So these are actually two different pieces of metal, and each piece is hooked up to one of the terminals on the galvanometer, or whatever you want it to power with this. One right now, let's just say it's positive. It's making the other one negative. 180 degrees later, as we've gone through the loop, that left brush is now going to be negative. But look what happened. It's now touching the other piece of metal. So the other piece of metal before was touching the right brush, which was negative. Now it's the brushes have switched, but so have the pieces of metal. Spin it again. The left brush is back to positive, and it's touching the piece of metal it originally was. And what that means is we get that pulsed DC current like you saw before.